In this recording, we are going to discuss parallel vectors. It says parallel vectors do not intersect each other. That means they don't cross paths. They don't touch each other at all. So no matter how long they are, they don't intersect. They don't cross paths. It goes on to say the distance between them will always be the same. It is also correct to say that they have the same gradient. Although vectors that are in the exact opposite direction are parallel to each other. Okay? The following diagram shows a visual representation of some pairs of parallel vectors. So as you can see, red and blue are parallel, orange and brown are parallel, and purple and brown, well, orange and maroon, sorry, are parallel. They are both going in the same direction. However, although purple and brown are opposite, that means they're going in the opposite direction. They are parallel because they have the same, they do not intersect each other. Okay, and the distance between them will always be the same. So here we have 3 pairs of parallel vectors. It is important to note that there are 2 main approaches to prove that 2 vectors are parallel to each other. One way is to show that they have the same direction. This can be done by finding the angle for each one, expecting it to be the same. So if parallel, theta 1, that means angle 1 and angle 2, meaning the direction of vector 1 is equal to the direction of vector 2, which are all equal to the opposite tan of y2 minus y1 over x2 minus x1. So if you calculate the direction of both, you will get the same value. So vectors u and v are parallel. Therefore, that's an example in the diagram above, in the previous slide. The direction of vector u and v is tan inverse of 6 over 4, which equal to tan inverse of 3 over 2, which equal to 56.31 degrees. So here we have a side-by-side view of the actual diagram and the calculation. So we know the inverse of the opposite over the adjacent. Okay, so for u, it would be 1, 2, 3, 4, 5, 6, because remember the angle is right here. Okay, between the vector and the x-axis. So this is the opposite angle, opposite side, sorry, that's 6 over 4. That's for u, inverse of 6 over 4. And that should be equal to the inverse of 3 over 2 for v. V, where is v? Look, v. So it's 1, 2, 3, right? Over 1, 2. Opposite over adjacent. So the inverse tangent of 6 over 4 is equal to the inverse tangent of 3 over 2, which is equal to 56.3 degrees. So their angle, their direction are the same. So therefore now they are parallel. Another way to show that one vector is a scalar multiple of the other, that's another way to show a vector is parallel to each other. That one is a scalar multiple of the other. For example, if vector AB is parallel to vector CD, and AB is equal to A over B, and CD is equal to C over D, therefore, vector AB, which is A over B, is equal to a scalar multiple, a scalar value, which is a number, times CD, which is K times C times K times D, which is equal to K times C over D. So that's another way to show that a vector is parallel, is by showing one is a scalar multiple of the other. So therefore, u know must be a scalar multiple of v. All right, u is equal to 6, 4 units to the right and 6 units up. So that's 4, 6. Whereas v now is 2, 3. Okay. 4 is 2 times 2, and 6 is 3 times 2. So therefore, U is equal to 2 times V. Okay? So U is a scalar multiple of V. So therefore, U and V are parallel. And here's the calculation. U is equal to 6, 4. Okay? And V is equal to 3, 2. So therefore, U is equal to 2 times 3 over 2 times 2, which is equal to 2 3s, 6. So the 2 is factored out, that's a scalar multiple. And 2 times 2 is 4. So U is equal to 2 times V. Now I just noticed an error because when you are representing a vector in its component form, the X translation goes on top and then the Y is X over Y. So for U, it's supposed to be 1, 2, 3, 4 comes on top and 1, 2, 3, 4, 5, 6 comes below. Okay? The 6 on top and the 4 below was for opposite over adjacent for calculating the direction. But when you're representing a vector in its component form, you always put the X displacement above and the Y displacement below, X over Y. So by right, it's supposed to be U is equal to 4 over 6 and V is equal to 1, 2. That's X movement over 1, 2, 3. Y movement come below. Okay? And then U now is equal to 2 times 2, which is 4, and 2 times 3, which is 6. But then that 2 over 3, now when you factor out 2 over 3 is actually V. So U is technically equal to 2 times V. So U is a scalar multiple of V, therefore U and V are parallel. As I always say, an error is a learning opportunity. So it's not supposed to be 6 over 4. See, 6 over 4 is for the calculation of the direction, opposite over adjacent, Y over X. But when it comes to the representing a vector in its component form, you always put the X above and the Y below. Okay, so that's how it's supposed to be. So we have to delete this and replace it with this. As I always say, an error is a learning opportunity. And this is followed by vector exercise 9. Are vectors B and U parallel? So here are vectors B and U. So the question is asking if vectors B and U are parallel. Now you've got to show all working. And B, prove that vectors T and R, here it is the purple and the brown, prove that they are parallel. So you've got to do the same working like part A. Okay, so because you are learning this, I recommend that you do this both ways. Calculate the directions and prove that the directions, that means the tan inverse of opposite over adjacent is the same. And another way is to prove that one vector is a multiple of the other. So if they are parallel, U should be a multiple vector of B. Okay. And this U and not this U, the maroon U. And R should be a multiple, a scalar multiple of vector T, if they are parallel. So I will do both workings because you are learning the concept.